So one way to find the natural frequency is to use the Rayleigh method. And I'm gonna give you an example of a mass spring system. For example, if you have a spring here with stiffness K, the mass is here. So when you attach the mass, the spring deflects and it elongates. And this is initially the length of the spring is L, and then it deflects with the delta, L plus delta. So the formula here is the T represents the kinetic energy and big V is the potential energy. Any body which has, like, of course, the mass possesses kinetic energies, and the springs they store the potential energy. So when we have the free, like if I draw the free body diagram, so mg and k delta, they are this, they balance out. Delta is the static deflection. Delta we call as the static deflection. So the weight of the this mass is equal to the spring stiffness times the deflection, is the force or the weight. So the kinetic energy, it is equal to half m x dot square, which is half mv square, and the potential energy is combined with the gravitational potential energy and the spring strain energy. We call it as half kx. So the energy stored in the spring is represented by the formula half kx square, and the gravitational potential is due to the gravity mgh. In this case, if it is like x deflection, so it is mgx. The Rayleigh energy method is used to find the natural frequency of the mechanical system. So I can write down the formula here. The kinetic energy max plus the potential energy min. This is equals to the kinetic energies minimum plus the potential energy maximum. So T max equals to what? T max half mx dot square, and T min is 0. And what is V max? So V potential energy half K X max plus delta square minus mg x.
Isn't X max X plus delta though?
X max is the maximum position when suppose vibrate starts vibrating. This is my X max. X is a instantaneous position. So we have to collect the maximum. Um, for example, it goes up until the maximum position and the kinetic energy becomes 0. It becomes at rest. When it is at extreme position, it stops there and comes back to the equilibrium position, and the mass goes beyond the equilibrium position because of inertia and starts vibrating about the mean position. So maximum position, you have the V max, but T min is 0 because it stops there. You understood that point? It stops when it has reached the maximum downward motion or maximum deflection. And I would say you can also write down the this formula. I want to say one thing here that you can write down x as a simple harmonic motion, and what is x dot equals to? That is also equal to a times x. So I'm gonna start from here. V max equals to V max. This is my V min. And V min is the static deflection. So I would say V max, this is also max. So this is this equal to this one. So I can write it down like half m x dot square V max is half k x plus delta square minus mg x and minus half k delta square. This is for this position. So if you open the parentheses, so if you do the math here, half k x m, I would say k. xm is cancelled by this. We know that mg equals to k delta. So this is cancelled by this. So you're left with this only, this term. On the left hand side, this is half m x dot square. And half is cancelled by this one. So I can write down in place of this one, I can use the simple harmonic motion. How can I replace this? This is a omega x. Sorry, I should have written here. Let me rewrite here. This is a, sorry, a x omega or omega x. It doesn't matter. So can I write down m in place of x dot? I can write down omega x in the mod x square equals half k x square. Sorry, half is cancelled. So what I'm left with, if I open the parentheses, so x square is cancelled by x square. So I'm left with, which is the natural frequency. This omega n is also the natural frequency of the mechanical system.
We got the same results a lecture ago. Is this different for natural frequency?
This is a different method. The lecture ago, if we see, this is a different method. So I wanted to teach you another method, that the Rayleigh method, which I have to cover in this chapter 3.
Okay.
Yes, I believe yes. So let me show you one more thing here. Three point three one. Let us solve this problem. Now I will apply the Rayleigh's method to find out the natural frequency of this simple pendulum. So T max equals to V max minus V min. As you know, it stops here, so T min equal to 0. So if we rearrange the Rayleigh's energy equation, this looks like this equation. And if I show you that the T max of mx dot square, and if you take a look here, so if this is suppose arc length, so what is this? X equals to L theta. So if this is X, X is equal to L theta, and X dot equals to L theta dot. So if you plug this over here, so I can write down L theta dot square or equals to T equals to half M L square theta dot square, and the potential energy. So there are two types. In this case, the potential energy minimum. Suppose this is my datum line. So V min is also zero in this case. So this goes to zero. So V max is my, so if I zoom in, so suppose this is my position for maximum gravitational potential energy. So that is equal to mg. This is my h. So h is, suppose this is my length. The length of the pendulum is this one, and if you do the, if this is theta, so this side of the triangle is L cosine theta. So if I want to find out the h, look, h equals to the total length, which is L, minus this side of the right angle triangle. So L minus L cosine theta is the uh, length or the height. So I can write down the potential energy maximum mgl 1 minus cosine theta. Now here comes some linearization, that we have to do some linearization. For cosine theta, we assume that for small angle that is equal to 1 minus theta square over 2 factorial, and sine theta is for small angle can be represented by theta. So I'm going to replace this by the linearized model of cosine. So I want to eliminate cosine and just write down theta. So look, over here I can write down 1 minus 1 plus theta square over 2. You got my point? So 1 is cancelled by this one. So this is my V max. So T max, we already found this one is over here. So half M L square theta dot square is on the left hand side. Mg L theta square over 2 is on the right hand side. Now I want to find out that what is theta in simple harmonic motion. So simple harmonic motion, we can assume that the angular displacement can be written like sine wave with the magnitude amplitude a sine wave. So theta dot can be represented by a omega cosine omega t. So I can represent this, and similarly if you take the double derivative, you will get negative a omega square. So if you focus on the amplitude here and plug it in over there in this equation, the amplitude half ml square Over here, the amplitude is written here, a square over 2. So don't worry about writing the sine and cosine function. Just pick the amplitude and replace by theta or theta dot to simplify your answer. And then if you do the math here, you are left with m is cancelled by this m. This is omega is actually the natural frequency. So so 1L is cancelled by 1L, half is cancelled by half, a square is cancelled by a. So you're left with omega n square equals to G over L. And if you take the square root on both sides, omega n equals to G over L. So will you be able to find the natural frequency of similar systems? I'm going to assign you some homework problems that you will practice from chapter 3. And I haven't graded your quiz yet, but I'll be able to grade soon, probably by the end of this week. How about your project ideas? Are you still working on the project ideas? That's good.
Yes. Um,
That's good.
what are we trying to do with the projects or the yeah.
The project is required like 15% of our grades. And I would like you to write down like start writing with the semester along the semester. This is spread all over the semester. So you will have plenty of time to write down the first portion of introduction. First, we select the ideas. I will take a look on the ideas, and then we will pick one idea and start working and doing some research what other papers have written down. We will do the literature review and try to start writing our on a paper. So we will use our MATLAB script to find out some results from the formulation which we study in this book or over the internet. Some search you have to do, that is your work. So first we come up with the ideas. So it's not just like 2 weeks progress report, it's spread all over the semester. So we will go slowly. First, we write down the literature review, and then we will further modify our abstract looking at the literature review, what you can put your work into this old projects. For example, someone has found the damping coefficients with the what we call the damper and the vibration amplitudes, and you want to add some more parameters, and we will see how can you add more parameters by using some theory. Either we haven't studied it yet or we are still studying it, it depends. So what project, some people take the noise reduction or some people take the project regarding the damping coefficients and vibration reduction in the cars. Or so we will try to see how can we find certain results. This will improve your what we call the professional writing skills and give you credit for the project.
So we were thinking, I think chapter one we discussed the spring damper system for a car suspension. For the MATLAB scripts, would you take that system and just model it over several different roads and then design the system to damp really fast, for example? Are we designing something or just kind of analyzing
Yeah,
it?
this can be a design project as well. You are right. So we can design a damper and using our theoretical knowledge, this can be a possible if you have different roads structure like bumpy road or even roads, how can you make your damping coefficients regarding that road. We will talk more once I read the abstract, and I'll give you my feedback about it.
All right, thank you.
All right, so you have done this one. Let's do one more problem here. Yes, we will use the amplitudes only. We will not use the sine and cosine function for simple harmonic motions. So the question was asked, why don't we use sine and cosine in place of the angles? So we will use this the maximum amplitude. This is just like the the amplitude is going to be replaced here. Don't worry about the sine and cosine waves. So let's do one more problem. This will more clarify your concepts. This is a rotational case plus translational. The question is asked, apply the Rayleigh's method to determine the natural frequency of the cylinder shown in the figure. So before I start this one, I want to show you this any body which rotates, and of course the rotational um, velocity is omega. So the kinetic energy in the displacement, like angular displacement, can be written like half I omega square. Or in terms of theta, I can write down half I theta dot square is in rotation. And kinetic energy in translation can be written like half m v dot or x dot square. Imagine this is my position, equilibrium position. So x equal to 0 in our equilibrium position, and when this rotates like theta, so if this is like x here, x is equal to r theta, and theta equals to x over r, and we know that omega, we wrote down over here, omega is equal to theta dot, which is omega x dot over r. So if I take a look, this is, suppose this is my h, This is my X, so it's like a big triangle if you take a look. So what is H over X in right angle triangle? This is like a opposite over hypotenuse equal to sine P, or H equals to, if you just simplify this, sine phi. So if I write down mgh, which is also equals to k times delta, can I write down like mg sine uh, mgh k mg sine phi. So let me write down here. There is little mistake. This is mg for equilibrium. I will say m k delta equals to mg sine phi. So this is like a mg sine phi when it is released from this position, so that is static equilibrium. That's what it is. The the strain energy equals to half k x plus delta whole square minus mg h, and v min, this is for v max, so I can write it down here. So v min equals to half k delta square. So can we, if we just, this is our v max, if we just open the parentheses here, x square plus delta square plus 2x delta minus mgh. So let me draw a line here, mgh, or h equals to x sine phi here. And after you do the simplification, what you guys get here, so let me write it down here, half k x square plus half k delta square plus x, I would say kx delta, kx delta minus mg x sine phi. So mg sine phi, can I write down this one like k delta x, because we know that mg sine phi equals to k delta. So k delta x is cancelled by this k delta x, so you're left with this. These are the two terms for our Vmax, the potential energy maximum, and Vmin is this one. So we know the formula for the Rayleigh energy method. This formula T max equals to Vmax minus Vmin. So T max is the combination when this cylinder moves downward, it rotates plus translates. So that's why I mentioned there are two types of kinetic energies we have to consider here. One is due to the translation, one is due to the rotation, or I can write down in terms of theta dot square. So I can plug it in over here. T max equals to V max minus V min. And let's plug it in everything here. Half m x dot square plus half I theta dot square equals to half. I can rewrite this T max. This is my T max. Okay, T max in terms of x dot. Can I replace this by this theta x dot or r? So I can replace this by x dot or r square. So I can rewrite here half into m plus I over r square x dot square. So now we have everything ready. So now you will assume that simple harmonic motion can be written as a sine omega nt. So we take the amplitude here and plug it in over here. So half m plus I over r square a omega n square. On the right hand side, if I just half kx, if I just pick this one, so on the right hand side, let me write down over here. So the negative sign, because V min is half k delta square. So I can cancel this out. So this is my half k delta square. This is cancelled. So you're left with only this term on the right hand side, that is equal to half, I'm sorry, the half k x square. The amplitude of x is a square. A square is cancelled by a square. So if I write down split it like this, and half is cancelled by this half. And if you take the square root on both sides, so you're left with this formula. So this is your answer for the natural frequency. Now, after we have learned this section, I have given you three examples to do the Rayleigh energy methods. I'm gonna give you some homework problems to practice. You may see similar problem in your quiz, coming quiz. Probably not this Saturday, but the following Saturday you will have another quiz from this chapter, and or maybe a test. If I believe I should give you a test the following Saturday. So I'm gonna assign you this homework problems. So we are skipping chapter 2, which will come back for the dynamics portion later down the road. But let me finish the vibration portion first. So the test 2, I will look into the syllabus and email you. Okay, I'll email you what you have to prepare for the test 1, as well as yes, test 1 will be probably, yeah, email about the homeworks. So let's do one more section. I'm gonna solve one more section here. Free vibration with viscous damping. The next section is free vibration with viscous damping. So let me copy paste the figure here. As you can see from the free body diagram, that this is the Newton's second law. Newton's second law. I'm sorry, this is, and the the damper force is, there is a friction in the contact surface that can be assumed as a damping coefficient, and you know that the damping force is c times velocity, or x dot. Now assume, let's say the solution is a e to the s t. So I want to plug this x double dot. What is x dot from here? A s e to the st, x double dot a s square e to the st. So let's plug in x dot and x double dot, x dot and x double dot into this equation, and then see what are the roots of s. So if you find the roots of s into the solution, then we will see three cases. I'm going to show you first case, second case, three cases. So let's go slowly and plug in x dot and x double dot into this equation 3.4-1. So I will just remove the parentheses here, m a s square e to the st plus c a s e to the st plus k a e to the st equals to f. So let's take this one, it's common. So a e to the st, take it outside the parentheses. So ms square plus cs plus k equals to f. Let's assume there is zero force, input force, just like initial conditions. So what it happens that there are two factors here. So this one cannot be zero. Why? Because if the amplitude is zero, what will happen? It is at rest. The mass is not moving at all. That's what it means. But this is not the case. It is moving back and forth. So this cannot be equal to zero. Only this thing can be equal to zero. So if we do this and equal to zero and use this formula, you remember the formula for minus b for quadratic formula. You remember x equal to minus b plus minus b square minus 4ac over 2a. So use the same formula over here to find out the roots of this quadratic equation. So minus c plus minus c square minus 4mk to m. So based upon this formula, these are the two roots of the quadratic equation. So you will see, I'm gonna just show you the graphical representation of three cases. What are the three cases? So let me show you. So it depends. If if the discriminant um, c square minus 4mk, if it is positive, then it is the overdamped case. Overdamped. Then real roots. But if it is if this is negative, then it is underdamped case. And if this is equal to 0, it's a repeated roots, it's a critically damped case. So let me show you, if we have initial condition to this mass, okay, this mass, if you move it to the suppose 2 centimeter to the right and just leave it, it will come back to original position, which is at rest. This is suppose 2 centimeter. Suppose this is a or 2 centimeter here, and you leave it over here. So if it goes like this and starts oscillating, comes back like this. This is the, when you see oscillation about this mean position, this is my mean position, okay? When you see the oscillation, this is known as under damped case. So S is complex roots, like a real plus imaginary roots. Or in our book, they have written down like a complex conjugate. In terms of real, can be written like R, letter R, plus minus imaginary times Q. So if there is another case, if you leave this mass here and it comes slowly and to the mean, it does not oscillate. And another case is, and when it is very slow response. So I have drawn three cases. So this is my case one. I would say case two, case three. So this is my case one, case two, case three. One second. Yes, this is correct. Under damped case, you have a complex roots in case of underdamped case. So these roots, if you draw, this is usually the Laplace plane, real and imaginary plane is also known as the Laplace plane. So if you see the complex roots in the form of iota q or jq minus jq or iq, this is the real part. So if you see the complex roots, which are always present in terms of complex conjugate pair, then this is the case of underdamped system. And if you see multiple roots, this is the case of overdamped system. And if you see the repeated roots on top of each other, okay, then this is the case of number one. Let me check. Overdamped is critically damped. So this is number two. So in number two, this case means that the two roots are equal, and there is a formula. Let me show you the formula in order to find out the solution. So the solution for case one. So let me explain to you for case one, overdamped case. We also call it zeta. Zeta is nothing but damping ratio of actual damping to the critical damping, and it can be written that the displacement of this mass can be written like a coefficient, unknown coefficient, real a to e to the real m2. I did not write down q term, like this terms goes zero because in overdamped case I just mentioned you don't see the imaginary part. So s1 and 2 both are r1. I would say let's separate s2 equal r2. So you just plug it in. And in case 2, critically uh critically damped system. So I would say critically or zeta is equal to 1. That means c equals to cc. So in that case, repeated roots, the formula for the solution for the displacement for this mass, the displacement at any instant, the displacement, like this is our degree of freedom, can be modeled as this formula. In MATLAB, you can also see this in MATLAB, R1T plus T a to e to the r 1t. You see, r1 is again coming into the next term, so that's a case of repeated roots. And case 3, underdamped case. And it is true, you will see that s is r plus iq. I would say s1 r1 iq1 s2 r2, sorry, r complex conjugate. R is same. You don't need to write down the sub for R1 because R1 does not change, only the Q values changes. So let me write down the solution for this one. At any time, you can trace the displacement of the underdamped system by this formula, A1 e to the R plus I Q T. So e to the RT is outside the parentheses. So you are left with A1 e to the IQT plus A2 e to the negative IQT. It can also be represented by one line, one term with this formula B e to the RT sine QT plus V. Let me make sure the students are oh students are watching. Can you guys hear me? I see some people are like leaving. Can you guys hear me and see the screen?
Yes.
Online screen. Okay, thank you. So this is another equation to represent the same equation. Now I have shown you three formulas. I want to show you a table. So what is B? What is Q? You might see similar problems. So let me show you the table in our book. So if I go to this book here, yes. So these three cases, they are written in this table. So it's a very helpful table. So what is, if this is a case one overdamped case, you will use this solution. And how can you find out A1? This is given. A1 can be found using this formula. And case 2 is the critically damped system. When both roots are equal, you can write down this formula to model the displacement in this form. And case 3 is the complex roots. Sine and cosine function can be written like this uh, equation, and where phi equals to this one and b equals so let's do one problem. The problem is obtain the free response of the following model. So the initial conditions are given. The displacement at time t equal to 0, it is 2, and velocity at time t equal to 0, it is 5. So let's do this one. So this is similar to like mass spring damper system. So ms square, I can write down here like mx double dot plus cx dot plus kx equal to 0. So if you compare our standard mass spring damper system with this equation, this so the mass equals to 2 kilogram, damping coefficient equals to 10 Newton second per meter, and k equals to 8. So if you find out the roots of this equation, so if I go to the MATLAB, and so I can write down in terms of 2s square plus 10s plus 8 equal to 0, because I assume that x equal to a e to the st, because e to the st is like a sinusoidal function, because you remember um, e to the x equals to iota x equals to cosine x plus iota sine x. So I'm not going into the detail, but this is the sine cosine functions, just simple harmonic function. So if I go to the MATLAB, I can plug in this equation, this function, and use the same equation in the descending order of the degree. First, you will write down the coefficient of the highest degree, which is s square, in this case 2. Then comes the second highest, then comes the third highest. So if I plug it in MATLAB, so let me see what do I get. So roots of the equations 2, 10, 8. So I got -4 and -1. If you plug it in MATLAB, you get roots s1 equals to -1, s2 equals to -4. And this is on the real axis on the Laplace plane. So this is -1, this is -4. So these are the real roots, which case is this overdamped case, okay? And in if we go to the table, real roots overdamped case, we will use this formula to find out the displacement. And for this one, I need to use this equation. So if I write down A1, I can write down A1 equals to V naught minus R2 X naught. So in our case, S1 just has the real part. So let's find out what is our A1. So V naught in our case, it is equal to 5, X naught equals to 2. So V naught equals to, I would say just 5 minus R2 is -4, X naught is 2. Divide by R1 minus R2, -1 minus +4. So what do you guys get for this one? 13, 13 over 3. And now let's find out what is A2. This is X naught, it is 2, 2 minus 13 over 3.
Isn't it 18 over 3?
It is 13 over 3, right?
Oh, never mind. Sorry. Yeah, 5 plus 8.
Yeah. So A2 equals to 2 minus 13 over 3. That becomes, let me, it is -7 over 3, correct? Please correct me if I'm doing some mistakes. You can help your professor. Okay, now x of t, let's use this formula. So this formula, it is a1 e to the r1t. So let me write down a1 e to the r1t plus a2 e to the r2t. So a1 we already gotten 13 over 3 e to the r1, which is -t, and a2, which is -7 third e to the -4 t. So this is your solution. So if you show me like this in your homework problems or quiz problem, you should get full credit for finding the solution of the quadratic formula and these cases. Have you guys understood? The next thing is they are asking you, if you take a look, they are asking you to do the same thing for when the case like initial conditions are different. initial conditions are different here. Okay, so you will do this at home and practice for this case. The since we have a few more minutes, so I just want to show you the solution here. And if you plot this in MATLAB, you will see three cases like this. You can make your own time vector in MATLAB. Everybody understand like how to make a time vector like from here. If you do like from 0 and then point maybe point 1 1/10 to 4 seconds, this will give you the time vector, and you can plot it in MATLAB using this in MATLAB. The script will be written like this: e times exponent negative t. If you call in the time vector here, exponent e to the negative 4 times t. So this is how you will plot this in MATLAB to find graphical solution of plot. Plot command can be written like this: plot x times t, and then you hit enter. So I think I knew you have understood MATLAB. If you don't, if you want to refresh, if there are some tutorials available online, so I would highly recommend you to go with it. This will be useful for your project as well as for your homework problems. Then comes the equation, another formula here. I don't want to solve it, but I just want to show you how this problem has been solved here. This is the same problem, but now the roots are repeated roots, and then you can use the same table for the repeated case to find out the unknowns a1 and n2. So the next topic, since we are short of time, but I would make small video for the Laplace plane. This is just the conceptual part. So what I'm going to show you, this one, analysis of the characteristic roots. So if you do the analysis in the Laplace plane, I have kind of alluded it to you earlier that if the roots are on the real axis, how would the response look like? So let me show you this table. When you go home, you can understand this. These are the responses. Like if this is mass spring damper system, these are the responses. So just one example. Let me show you. This is like a real sorry, this is like a, so here, if I draw it here, look, this is the imaginary line, this is the real line. Okay, it's like a Laplace plane. Laplace plane consists of real axis and imaginary axis. So if the roots are in this domain, like complex domain here, complex domain here, you see oscillation. But here, this is lying on exactly on the imaginary axis, means there is no damping. If the roots are lying on the if the roots are lying on the right hand side of the imaginary line, they will grow. This is unstable system. I would say unstable system roots, like uh, roots are s1 s2 are positive real part. If you see positive real part, then this is positive is not good. You see negative real part, it's a stable system. And if you don't see qt, if you just see if you just see uh, r1 r2, this is on the, yeah. And if you see just the imaginary part, no real part, it means no damping. So it's just the basic thing. We will talk more about it later on. Thank you guys. I'll see you next week.